Okay, this section we're going to call roots and radicals. This symbol here is a radical symbol. It's always positive unless otherwise indicated. And so you could always assume there's a plus out here. We have a radical. You'll see a value under there, like 8. And you might see a value out here, like a 3. This is called the index, and what's underneath the radical is called the radicand. That's your radicand. And when you have, in this case, if we were to read this, this would be the cube root of 8. Right? It would be the third root of 8. And what that does, it asks a question. It says, what times what times what will equal 8? Where that these 3 factors are the same. Right? So we're looking for what 3 values multiplied repeatedly 3 times will give me 8. And we all know that 2 times 2 times 2 is equal to 8. And therefore, we could say the cube root of 8 is equal to 2. In this example, we have a radical 9. But we notice that there's no index here. Index. There's no index over here. And when there's no index, this is assumed to be a 2, or the square root of 9. So when there's no index, assume that it's a square root. Assume there's a 2 in there. So, just to bring us back, I said this is a radical symbol, which is true, it is a radical symbol, but when it has no index, this could also be a square root, right? Because there's no index indicated, that's a square root symbol. So here I have the square root of 9, so it's asking what times what will give me 9, where these 2 values are the same. So we know the square root of 9, we know 3 times 3 is 9, therefore the square root of 9 is 3. What if I have the cube root of negative 27? Right? Again, what times what times what will give me negative 27, where these 3 are the same. And we know a negative 3 times a negative 3 times a negative 3 will give me negative 27. So this is negative 3. Cube root of 27 is negative 3. What if I had radical, well, let's make this a negative 25. What if I had the square root of negative 25? Right, there's no index, so this is a square root. So this is asking what times what will give me negative 25, where these 2 factors are the same. right? I know 5 times 5 is 25, and negative 5 times negative 5 is 25. The only way to get a negative 25 is if I have a negative 5 and a positive 5, if the two signs are different. And if the two signs are different, then this is not going to be the same factors. So right now, we'll say this is not a real number. This is not in our real number system. It's actually an imaginary number, which we'll talk about later. But it's not a real number. Let me turn the page. So on this page, we have some examples. I'm going to ask you to evaluate. Evaluate, again, means find the value. So let's take a look at these, and I'll go through them all. Oops. Let's see what we got there. Yeah, that's all of them. So right now you might want to pause this video and try these, and then come back and see how we did them when we do them together. So I would suggest you pause the video now, unless you want to see me go through these. Square root of 36. Square root of 36 is asking what times what will give me 36. So I know that 6 times 6 is 36. So the square root of 36 is 6. In this next example, it says negative square root of 49, the negation of the square root of 49, or we could think of this as kind of like a negative 1 times the square root of 49. We want to do the square root of 49, which is 7, and the negation of that, or negative 1 times 7, would be negative 7. Right? When the negative is on the outside, it's multiplication. In this example, the negative's on the inside. So this, again, is saying what times what will give me a negative 100, but the two values have to be the same. And there are no two values that are the same that'll give me a negative 100. So this is not a real number. It's imaginary. In this next example, we have the square root of 144 plus 25. So it's the square root of this entire value. So we could simplify that. Instead of writing 144 plus 25, we could write this as the square root of 169, which is a perfect square. What times what will give me 169? I believe 13 times 13 will give me 169. Here, this one's similar, except for we have two different radicals, right? So we're not going to add them initially, we're going to add them after we find the value. So here I have the square root of 144, which we know is 12, because 12 times 12 is 144. And square root of 25 is 5. And then we would add them. So my answer is 17. The square root of 144 plus the square root of 25 is 17. It's 12 plus 5. In this next example, it's the cube root of 64. I'm not sure how comfortable you are with your cubes, but you might want to list your cubes. You know, like 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. 4 times 4 times 4 is 64. 5 times 5 times 5 is 125. And we could probably stop there. So you know that you have a few cubes. These are perfect cubes. 1, 8, 27, 64, and 125. So the cube root of 64, well, again, we know 4 times 4 times 4 is 64. So the cube root of 64 is 4. Similarly here, 125, I know negative 5 times negative 5 times negative 5 is 125, or rather a negative 125. So therefore, the cube root of 125 is negative 5. And you might notice that anytime you have an odd index, you can have a negative underneath the radical. Right? Your radicand can be negative. But anytime it's even, right, like a square root of a negative, where was our square root? Square root of a negative, you cannot have a negative value underneath the radicand. So like in this example, I have the fourth root of negative 81, right? And negative 3, well, I know 3 times 3 times 3 times 3 would give me 81. But if they were all negatives, it would give me positive 81. And if they're all positives, it would give me positive 81. So this isn't going to work. This is not a real number either. And in this last example, it says the fourth root of negative 2 to the fourth. Okay, so here what we could do is I want you to look at this two different ways. We could do what's underneath the radical first. So a negative 2 to the fourth is really negative 2 times negative 2 is 4, times negative 2 is negative 8, times negative 2 is positive 16. So this is really saying the fourth root of positive 16. And the fourth root of positive 16 is 2. So really what we could do when we have the fourth root of the fourth root like this, anytime it's even, we could cancel these out, right? And we would get the absolute value. It would always be positive because it's fourth root. So they write this as the absolute value of the radicand. So for example, if you had the, again, we'll do fourth root, but if you had the fourth root of x to the fourth, of some number to the fourth, this will always be equal to the absolute value of x, right? So if this x is negative 7, if it's the fourth root of negative 7 to the fourth, then my answer would be the absolute value of negative 7, which would be positive 7. So when you look at the answers, sometimes in the back of the book they'll have absolute values around variables, because in this scenario it's always the absolute value. It's always going to be positive. What about when it's odd? If I had the cube root of any value cubed, it would just be that value. In that example, we could have a negative. As we move forward, we're going to start simplifying radicals, because when we have the square root of 9, right, we know the result is 3. This is a rational value. Right, we lose the radical. 3 is an integer. It's nice. But if I had the square root of 8, right, the square root of 8, I'm asking what times what will give me 8. And there are no two integers that multiply together that will give me 8. I have no two values that I could multiply together to give me 8. I could estimate it, right? I could get an approximation. Right, if I plug this into my calculator, and the square root of 8, it's going to give me a decimal approximation. I don't know, I think of 2.8. So it's an approximation, it's not the actual value. But what we could do when we have the square root of 8 is we could simplify the radical. We could break this up into the multiplication of two values, two radicals. And what we want to do, since we're simplifying, we want to find something that's going to be rational, something that's going to come out of the radical. And the only thing that would come out of a square root is a perfect square. Perfect squares are 1 times 1, which is 1, 2 times 2 is 4, 3 times 3, 4 times 4, 5 times 5, 6 times 6, 7, 8, 9, 10, 11, 12 times 12, 13 times 13, 14 times 14, 15 times 15. These are all perfect squares. So what we want to do is we want to find the largest perfect square that goes into 8, which in this case would be 4, times what value will give me 8? Right? 4 times 2. So we want to put our perfect square to the left and our throwaway to the right. Right? So, and now we could simplify it. So we all agree that the square root of 4 times the square root of 2 will give me the square root of 8. But the square root of 4 could be simplified. Square root of 4 is 2. Square root of 2 cannot be simplified, so I could just bring that down. So the square root of 8 in simplest radical form would be 2 rad 2. And that would be the exact value. It's 2 rad 2. So let's try some more. Let's try the square root of 50. The square root of 27. The square root, let's do something harder, like the cube root of 16. Maybe the fourth root of 80. And then we'll end with the square root of 72. I suggest you pause it. Pause this video right now. Try these problems out and see how you like it. See if you can make it through, and then return and we'll go over it together. I'm going to go over it right now. So the square root of 50, there is no square root of 50, so what I'm going to have to do is I'm going to have to break this up into 2 radicals. I'm looking for the largest value that will go into 50, the largest perfect square that will go into 50. I know 25 goes into 50. I could write this as 25 times 2. And the square root of 25 could be simplified. 5, and I have radical 2. Similarly, the square root of 27, there is no square root of 27. So what's the largest value that goes into 27? Start on the high end and work backwards. 36, 25, 16, 9. This could be broken up as the square root of 9 times the square root of 3. 9 times 3 is 27. 9 is a perfect square, so I could take the square root of 9, and then I could bring down my remaining factor, radical 3. So 3 rad 3 would be radical 27 simplified. The cube root of 16. Now the cube root, now I got to think about cubes again. So what are my cubes? 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. Well, I've already gone too far because 27 is too big. And I know that 8 could go into 16. I could rewrite this as the cube root of 8 times the cube root of 2. Cube root of 8 times the cube root of 2 is the cube root of 16. 8 times 2 is 16. And I could simplify the cube root of 8. This says what times what times what will give me 8. 2 times 2 times 2 will give me 8. And then I could bring down my remaining factor. This one comes out to 2 cube root of 2. Make sure you include that cube root, because if you don't write that index, it would mean that it's a square root, right? When there's no index, it means it's a square root. So you have to always remember to include your index. Here we have a fourth root. I don't know my fourth root so well, so I'm going to write on the side 1 times 1 times 1 is 1. 2 times 2 times 2. 2 times 2 is 4, times 2 is 8, times 2 is 16. 3 times 3 times 3 times 3. 3 times 3 is 9, and 9, that gives me 81. So these are my perfect fourth roots. And 81 is too big, so I'm going to go with 16. The fourth root of 16 times the fourth root of what will give me 80, and I believe the answer is 5. Well, not the answer, but for that one, right? 5 times 16 is 80, and the fourth root of 16 can be simplified. It's 2, and the fourth root of 5, my remaining factor just comes down. Lastly, we have this square root of 72, which I'm going to put on the other page. The square root of 72 is interesting because if I said, what's the square root of 72? Square root of 72 in my class, I would have inevitably somebody who gives me 9 and 8. And then usually I write 72 a second time. And everybody asks why I wrote it 2 times. And it's because 9 and 8, although that breaks up well and 9 is a perfect square, I like to find the largest perfect square that goes into 72. And 9, although it's a perfect square, it's not the largest perfect square that goes into 72. The largest perfect square that goes into 72 is 36. I could rewrite this as 36 times 2, which is 6 rad 2. So we want to try to find the largest perfect square. This will still work, but this is kind of like when you reduce a fraction and you don't use a large enough multiple. Like if you keep doing it by 2, you do it over and over again. So here we could do the square root of 9 is 3, and here we have a square root of 8. Well, the square root of 8 could be simplified further, right? 8 could be broken up as 4 and 2. So really what we have is 3 times radical 4 times radical 2, which is 3 times 2 radical 2, right? 3 comes down, square root of 4 is 2, and radical 2 can't be simplified. So I'm left with 6 rad 2. So I still come out with the same answer, and it's still correct, but it's a lot more work if we don't use the largest perfect square available. So ideally, you want to use the largest perfect square. So now you could simplify radicals as long as there's a value underneath them. What if there's a variable? Right, let's look at variables. What if I had the square root of x squared? What's the square root of x squared? Well, again, that's asking the question, what times what will give me x squared? And we know that x times x would give me x squared. Therefore, the square root of x squared is x. Right? What if it said, what's the square root of x to the 6th? Well, I know x to the 3rd times x to the 3rd is x to the 6th. Remember, you have to add exponents when you're multiplying. So the square root of x to the 6th is x to the 3rd. Well, what about the square root of x to the 10th? Or x to the 12th? Or x to the 50th? Well, the same thing for all of these, right? I know x to the 5th times x to the 5th will give me x to the 10th. So this is going to be x to the 5th. X to the 6th times x to the 6th will give me x to the 12th. And x to the 25, right? If I have x to the 25 times x to the 25, I keep my base, I add my exponents, that's x to the 50th. Right, so we also notice that I used all even exponents under there. When I take the square root of an even exponent, right, it's really just dividing them by 2. Right, 2 divided by 2 gives me 1. 6 divided by 2 gives me 3. 10 divided by 2 gives me 5. So those are pretty easy as long as you have even exponents. So now you would be able to do a problem that might look complicated, but wouldn't be that hard. You know, say you had, let's do an easy one first. 144 x to the 10th, y to the 4th, and z to the 2nd. Well, these are all perfect squares. 144 is a perfect square, and any even exponent is a perfect square. Right? So we could say that this is the square root of 144 is 12, and the square root of x to the 10th is x to the 5th, and the square root of y to the 4th is y to the 2nd, and the square root of z to the 2nd is z to the 1st. So my final answer is 12x to the 5th, y to the 2nd, z to the 1st. So if I had 25a squared b to the 14th, right, this is easy enough. The square root of 25 is 5, right? You want to recognize that this is a perfect square and have all even exponents, so they're perfect squares also. A times a gives me a squared, and b to the 7th times b to the 7th will give me b to the 14th. So those are relatively easy. We learned how to simplify radicals when we had an integer underneath, but what if I had the square root of x to the 3rd? What if I had a variable and it's not a perfect square? Well, if I have a variable and it's not a perfect square, I'm going to have to simplify it the same way we simplified the others. We'd have to break it up into 2 radicals, and we put our largest perfect square over here. What's the largest perfect square that goes into x cubed? I could write this as x squared and x to the 1st. Right? That would give me x cubed. I keep my base, I add my exponents. And then this could be simplified. Square root of x squared is x, and I bring down my remaining factor. So the square root of x cubed is x rad x. Try some more. Okay, what's the square root of x to the 7th? Let's do a bunch. Square root of x to the 8th. The square root of x to the 9th. The square root of x to the 10th. The square root of x to the 16th. The square root of x to the 17th. And the square root of x to the 20th. Oops. So why don't you pause it right now, try to do those problems, or if you want to see me do one more, watch this first one. I'm looking for the largest square that goes into x to the 7th, and that's going to be x to the 6th and x to the 1st. The square root of x to the 6th is x to the 3rd, and I bring down my remaining factor. So what we want to be aware of is x to the 7th, right, is not a perfect square. But x to the 8th is even. So in this case, I don't have to do all this to simplify it. The square root of x to the 8th is x to the 4th. Right? X to the 8th is a perfect square. We don't have to worry about it. X to the 9th is not a perfect square. It's odd, even though 9 is tempting. But we're looking for values that multiply together to give me 9. So in this case, I'm going to have to break this up as x to the 8th and x to the 1st. So I have x to the 4th rad x. X to the 10th is even. So that's an easy one. It's going to be x to the 5th, right? X to the 5th times x to the 5th is x to the 10th. 16, that's even. This is going to be x to the 8th. I wrote that funny. X to the 17th, I'm going to have to break that up. X to the 16th and x to the 1. I'm looking for the largest perfect square. The largest perfect square is 16, and then this would break up or simplify to x to the 8th and x. And lastly, this one's nice and even, so I have x to the 10th, right? X to the 10th times x to the 10th will give me x to the 20th. You all agree? I keep wanting to hesitate and give you some time to write it down, but you could always pause before moving forward, right? So say I had 300 x to the 5th, y, z to the 14th. And I asked you to simplify that. Well, the square root of 300, there is no square root of 300, so let's start by making our two sets of radicals here. Give yourself enough room. And then we're going to look at these one by one. We're going to look at the square root of 300, right? There is no square root of 300, so I want to break it up. What's the largest value or the largest perfect square that goes into 300? I'm going to say 103. Right? 100 is a perfect square. X to the 5th, is that a perfect square? No, x to the 5th is not a perfect square. But this could be broken up as x to the 4th and x to the 1st. Y to the 1st, is that a perfect square? That's not a perfect square, and that can't even be broken up. It's not a perfect square, so it goes over here with my not perfect squares. We're putting all the perfect squares to the left, all the non-perfect squares to the right. And then lastly, we have z to the 14th. Is that a perfect square? Yeah, that is a perfect square, so I don't have to break it up. I could just put z to the 14th over there. So now if we look, we have all perfect squares, 100, x to the 4th, and z to the 14th. Now we could simplify this. The square root of 100 is 10. The square root of x to the 4th is x squared. And the square root of z to the 14th is z to the 7th. And then we could bring down our 3xy. Awesome. That was fun. Let's try another. All right, let's do the square root of 36, a to the 7th, b to the 2nd, and c. All right, that's an easy one. Well, maybe I don't know how easy, but pause it if you'd like. Otherwise, I'm just plowing through this one. I'm going to create two radicals, square root times a square root. I'm putting my perfect squares to the left. I'm putting my throwaways to the right. So I'm going to look at these one by one. Here I have the square root of 36. Well, 36 is a perfect square, so I could throw that over here. That's good. A to the 7th is not a perfect square, but I could break that up as a to the 6th and a to the 1. b to the second is a perfect square. I'm going to put it over here. Doesn't have to be broken up at all. And c to the first is not a perfect square. So that's going to go to the right. Perfect squares to the left, non-perfect squares to the right. So I'm going to have 6a cubed b radical ac. Try a more challenging one, a cube root. Let's say, I don't know if you even have any cube roots. Let's try a cube root, just for fun. Let's do 32x squared y z to the third. Throw another one in there. Let's do a w. Sorry, it's out of order, but w to the 11th. If you'd like, put your w before your x if you want to go alphabetically. Right, and this is a cube root. We want to break this up. We have to think about our cubes. So it's going to be a cube root. Make sure you put a cube as your index. 32 is not a perfect cube. So what we're going to have to do here is we're going to have to break it up. We got to think about our cubes. 1 times 1 times 1, 2 times 2 times 2, 3 times 3 times 3, 4 times 4 times 4, 5 times 5 times 5. Those are my cubes. What's my largest cube that goes into 32? 8. 8 times 4 is 32. Similarly, with perfect squares, we want them to be even. They want to be multiples of 2. With cubes, we want multiples of 3. Anything that's if I have an exponent that's a multiple of 3, 3, 6, 9, 12, 15, then it's a perfect cube. So x squared is not a perfect cube. Y to the first is not a perfect cube. But z to the third is a perfect cube. And w to the 11th is not a perfect cube, but it can be broken up. I could break it up. What's my largest cube that goes in there? What's my largest multiple of 3? 3, 6, 9, 12. So it's going to be 9, w to the 9th, and then I'd be left with w to the 2nd over there. So it looks like I'm going to have the cube root of 8 is 2. The cube root of z to the 3rd is z. And this will give me w to the 3rd. And we're going to have the cube root of 4x squared y w squared. Would be my final answer. Right? And if I multiply it, like if I do, because it has to give me that 9, right? W to the 3rd times w to the 3rd times w to the 3rd. I keep my base, I add my exponents. 3 plus 3 plus 3 is 9. That's where those are coming from.